Yeah, that's fine. Okay, so real quick, very brief review. I want to kind of finish up our discussion of yesterday about inverses. So, real quick, somebody, what's the definition of a function? What makes a relation a function, Sam?
Like a function is, isn't it an equation where when x value is always, or when x value is always mapped to its own y value?
Okay, so yeah, now that's you got the idea. Somebody want to just change it to, I mean, it's right. Somebody want to just tighten up the language a little bit, yeah.
One x value is connected to only one y value.
Okay, good. So, and it doesn't have to be an equation necessarily, right? It usually is. For us, usually a function is, we're going to be dealing with functions that are where we have an equation that generates y values, output values for every input value. But it doesn't have to be, right? It could just be some ordered pairs that are linked together in a set or something too. But you're right, it's a relation where for each input value, there is exactly one output value, right? Okay, so what does that mean in terms of a graph? What test could we apply to the graph of a relation to determine if it's a function? The vertical line test, okay, good. Now let's think in terms of inverses. What's inverses sound complicated, but they're really quite simple. What is the definition of an inverse relation? What do you mean by opposite?
Where the relation,
The domain is now the range, and the range is.
Okay, good. So it switches, it interchanges the inputs and outputs, the domains and the ranges, right? That's it. That's all it does. Okay, so if an inverse relation is to have, if a relation has an inverse, in order for that inverse to be a function, what has to be true of the original relation? What test does it have to pass so that its inverse will be a function? The horizontal line test, right? Okay, that's going to make more sense very shortly. Okay, I mean, it probably already does make some sense, but it'll make, on a deeper level, it'll make sense here pretty quick. So first thing I want to do is I want to explore the inverse nature of these inverse functions, the relations we're talking about. So I want to practice. There's kind of a concept we need to be reacquaint ourselves with in order for this to really sink in. So let's just start off a little practice here. Let's just say we've got some function f of x that equals, let's just say it equals x squared x squared plus 1, and let's say g of x equals 2x minus 3. Okay? So what happens, I want to do what's called, remember talking about compositions of functions? Back in Algebra 1.
I remember that.
Okay, well, there we have it. Okay, so what we're going to talk about today, very briefly at the beginning here, I want to reintroduce or introduce the idea of compositions of functions. All that really means is a function of a function, right? So for example, if f of x is defined like this, and g of x is defined like this, then I want to know, for example, what is f of g of x? Any ideas? How am I going to do that? Okay, keep in mind that a function is just a rule, right? If we have an equation. So f of x, what's f of 3? 10. How'd you get that?
X squared plus 1.
So 3 squared plus 1, right? What's f of a? A squared plus 1. What's f of han? Well, han squared plus 1, right? Okay, well, the function doesn't know what's behind my hand. It doesn't care. It just knows that whatever it is, it's going to do that to it, right? So what if what is behind my hand is a g of x? What's f of g of x? G of x squared plus 1, right? Make sense? Okay, so That's what this is, right? I mean, we can go further than that, obviously, but at the first level, we're putting something into F, and it's gonna spit out that pattern, right? So we're gonna get something squared plus 1, and in this case, the something is 2x minus 3, right? Okay, so then we can square that out. How do we square that out? What's the rule for squaring functions? How would you guys do this? I just want to make sure you know the pattern. What do we do if we have 2x? Is it 4x squared minus 9? It's not, is it? Okay. What do we do? What do you think? What are we gonna do with that? It's not, I mean, not a big deal. I just want to know how would you do it? What would you do, Maisie, if you had to square that out?
2x.
Say it again.
2x.
You'd have to distribute it. Okay, so you'd write it out as something, as just two binomials?
Yeah.
Okay, so we know that whenever we square something, whatever's being squared, it's that times itself, right? Does that make sense? So this becomes 2x minus 3 times 2x minus 3, and then I could just distribute or FOIL, whatever you want to do, right? Okay, there is a little shortcut though that I think it's good to be familiar with. But let's look at something real quick, just a little timeout for a sec. So if we have something like a plus b squared. Sure, that's the same thing as a plus b times a plus b. But if we do the math, what do we get? If we distribute the a's, I get a squared plus ab, right? If I'm going to distribute the a first, and then I'll distribute the b, right? Does that make sense? Right? Okay, and then the two interior terms are like terms, and so we end up with a squared plus 2ab plus b squared. So that's the pattern that always holds, right? Whenever we square a binomial, a sum of two terms, it's always equal to the first term squared plus 2 times the product of the terms plus the last term squared. That's just a good pattern we do that so often that you can just kind of skip down and use that pattern. So for example, up here, when we do this, we don't really have to go through the exercise of expanding this out every time, FOILing it out every time. We could just write this as first term squared, right? The quantity squared, plus 2 times the first term times the second term. What's that going to be? What's 2x times negative 3? Kirk, what's 2x times negative 3? Negative 6x, and then plus the last term squared. What's negative 3 squared? 9. And then don't forget, we got that plus 1 at the end, don't we? The thing that sometimes people make a mistake with is when you square out a term that involves a coefficient and a variable, what is 2x quantity squared? What is that? It's 2x times 2x, right? So I've got the point I just want to make here is you have to distribute that exponent to both of the factors, both the 2 and the x if they're multiplied, right? Does that make sense? I didn't mean to make this into some big complicated thing, but this is just something I think I wanted to just get you thinking along those lines of using that binomial expansion pattern instead of having to go through the work every time of FOILing it. Okay, so then we end up with, what do we get, 4x squared plus, what does it be, minus 12x, everybody agree? Plus 10, that's f of g of x. Okay, now let's flip this around. Now let's do g of f of x. Okay. What do you suppose that's going to be then? Yeah, okay, good, because now g of x, if I put something in, g of hand is just 2 times hand minus 3, right? Well, if hand is f of x, then I'm just going to follow that pattern with f of x, right? So I'm just going to get 2 times f of x minus 3, which is what? 2 times f of x is x squared plus 1 minus 3. So what's that simplify to? What are we going to get? 2x squared plus 2 minus 3 would be minus 1. Okay, I want you to notice something. Did we get the same answers when we reversed the composition? No, pretty different, right? So f of g of x was different than g of f of x. Okay? All right, so let's look for a second at how we find inverses. Yeah. Okay, we have kind of a recipe, and it makes sense. You don't really have to memorize this because it just makes sense. If we want to find the inverse of a function f of x, what are we going to do? Well, one thing it's helpful to do is to turn that f of x into a y. Just write all the f of x's as y's, and you'll see why in a second. We know that, I've always taught this a little differently. I might even suggest that maybe you switch these around. This is what our book says. It doesn't matter. Either way is going to work. But I've always said substitute y for f of x and then switch x and y. How come? What's an inverse do? Yeah, because it's an inverse. That's what inverses do. They switch the x's and the y's. So you flip the x's and the y's, and then you solve for the new y. Well, what they have you do, it's fine. They have you solve for x in terms of y, and then switch the x and the y. And then your new y that you've isolated is the inverse of the original y, right? Because you found it by switching the variables, okay? So let's look at an example. What if we have something like, we're going to start off with f of x equals 3x minus 7, for example. Okay, let's just go through these steps. So what are we going to do? First step, write it in terms of y. So we'll make the f of x into a y. And now, I don't care which way we do this. It doesn't really matter. Let's go ahead and switch the x and the y first. When I switch the x and the y, I'm going to make this red. How come? Why do you think? If I flip these around, if I flip the variables around, I always make that red, so there's a clear distinction between what we started with and what we have now. Why do you think I made it red? Different equation, yeah. Because now this is the inverse, right? We flip the x's and the y's. All I've got to do is isolate y, and I find the inverse function. So what are the 2 steps in order to solve for y? What do I do first? Say it again, what do I do first? Add 7 and then divide by 3. Okay, so if I do that, what am I going to get? Y equals x plus 7 all divided by 3. Great. So that's telling me then that the inverse function, and that's our notation for an inverse. It looks weird. It looks like a negative 1 powered, but it's not. If I take a function raised to the negative 1 power like that, it always implies that we've taken an inverse. So the inverse function is equal to x plus 7 over 3. Okay? let's explore what happens if we do a composition of these two functions now, okay? Okay, so if there's my function and its inverse. Let's first do, how about if we do f of the inverse of f of x. So what's that gonna look like? So f tells us f of hand is 3 times hand minus 7. So f of f inverse is gonna be 3 times inverse, right? Minus 7. So let's simplify that. How can we simplify that? What do you think, Tyler?
Distribute 3 to all 3 values.
Okay, I could distribute the 3 to all values, or maybe I could even do this. Remember that if we multiply fractions, how about if I write 3 as 3 over 1? Now, look what happens here. I've got, how many factors do I have on the top of this product? So if I were to rewrite just this part of it right here, I'd get how many factors on the top? 3 times the quantity x plus 7, right? So 2 factors. On the bottom, I've got 1 times 3, so I might as well just call that 1 factor. And what can I do? I can cancel. I can cancel because I'm canceling factors, right? I can vertically cancel like factors. So I can do that. Then I also have this minus 7 tacked on here. So what do I end up getting? What does this quotient become? X plus 7 minus 7. What do I get? X. How about that? Well, maybe that was an accident. Let's flip it around. Let's do the reverse composition. So this time we'll take the inverse function of f of x. Okay? Okay, so the inverse function, let's see, what was that? That rule was the inverse function of hand is just hand plus 7, all divided by 3, right? So we're going to get hand plus 7 divided by 3, and this time hand is f of x, so it's going to be the quantity 3x minus 7. Okay, so what can I do in the numerator there? If I simplify this one. So remember, when we're simplifying fractions, it's probably good to review this. There are implied parentheses around the whole top and the whole bottom, right? So if I follow order of operations, I got to work within parentheses first. So my goal is always, and I tell this to my calculus classes, I remind them every time, because we get some doozies in calculus. If we get a really nasty looking function that has a bunch of fractions on the top and fractions on the bottom, our goal is always to just simplify the top into one fraction, bottom into one fraction, and then flip and multiply, right? Well, in this case, we don't have anything that complicated, but we still want to just deal with the top first, bottom second, and then see what we get from the quotient. So on the top, what do we get? So 3x minus 7 plus 7 is 3x over 3 is what do you know? Okay, not an accident. This is the inverse nature of inverses. They undo each other. That's the other really important thing to know about inverses. Their definition is, an inverse is what you get when you swap the domain and the range, but in effect what they do is they undo each other, right? So if I take the function of an inverse or the inverse function of the original function, I'm always just going to get back the x. They unlock each other. It's almost as if they are canceling each other out. just leaving behind the x. Okay? Does that make sense? Okay. And it works for, let's do one even that's a little more challenging. Let's do, how about this one? What if we start off with f of x equals x minus 2 cubed plus 5. So let's find the inverse of that. Let's go through our rules. What do we do first? Okay, say it again. Okay, so rewrite it in terms of y's and x's. So f of x becomes y. Okay, what's next? Kind of have your pick. Switch the x and the y. Why don't we go ahead and switch the x and the y and then solve for y? Okay, so this becomes an x, that becomes a y, that becomes y. Okay. All right, so now our goal is what? Isolate y. And remember, you know, this is, we have, I know this seems kind of elementary, but really all we're doing when we're solving is we're just going backwards through order of operations, right? That's how we isolate a variable or solve. So what's the first thing we're going to do to get the y by itself? Subtract 5. Okay, now what about the next one? This is a little weird. You guys haven't had a lot of practice with this. We'll do a lot more of this year. But what's the next thing I would do?
We need to distribute the power.
Okay, so I can't do that. I can't distribute the power because y minus 2 cubed is not the same thing as saying y cubed minus 2 cubed. What is y minus 2 quantity cubed really, what does it really mean? It's y minus 2 times y minus 2 times y minus 2. That's going to be a mess, right? But as we work our way up the order of operations tree, think what this says. It says first we're going to undo any addition or subtraction outside of parentheses. Then we're going to undo any multiplication or division outside of parentheses. Then we're going to undo any exponents, right? So the very next thing we have to do is actually deal with the exponent. Now this isn't really fair. I'm giving you a question. We haven't really talked about this stuff yet, but you can handle this. I mean, we'll come back to this later in more detail. How do you think you undo a cube? Okay, so yeah, we're going to take the third root of both sides. You undo something cubed by cube rooting it, right? Okay, so first step, we get x minus 5 equals y minus 2 cubed. Now we're just going to cube root both sides, and the cube root and the cube cancel. Just a little side note, why do you think they cancel? Because they're inverses. Yeah. That's really, we even kind of take advantage of this nature without knowing it. When we want to undo a cube, what we really are doing is just taking the inverse function of the cube function, right? So they go away, and then now we've got cube root of x minus 5 equals y minus 2. Last step, add 2. Okay, so we end up with then, the new function, or inverse function, inverse of f of x equals cube root of x minus 5 plus 2, right? Everybody buy that? Okay, how could we verify that we got it right? How could we verify that we did all that work correctly?
See if they cancel each other?
See if they undo each other. But here's the thing. You can't just test it one way. It has to work both ways for them to truly be inverses. Okay, so let's try f inverse. So what's our rule? F of x says we're going to f of hand says hand minus 2 quantity cubed plus 5, right? So if hand is f inverse, then we're going to get oops. Then I've got to substitute that in there, right? So that's going to be cube root of x minus 5 plus 2. So we got some simplifying to do, right? Top-down order of operations. We always start inside parentheses, right? So nothing I can do inside the black parentheses, but the next layer of parentheses, yeah, I can do some stuff. What is the cube root of x minus 5 plus 2 minus 2?
Get rid of x minus 5.
Get rid of the 2's. Okay. So what is the cube root of something cubed then? Cancel out. So I'm going to get x minus 5 plus 5 equals what? X. So it worked. It worked in that direction. Now we got to reverse the composition. So now we go f inverse of f of x. And what do we get? Well, we have our rule for f inverse. F inverse of hand is just the quantity hand minus 5 cube rooted, right? Plus 2. So what goes in there? Well, f of x. So what can I do? Following order of operations, we have to work inside parentheses, but parentheses really means grouping symbols. Right, so what can we do? Well, if we look inside the grouping symbols from the most inside, x minus 2 can't be simplified. Even inside the black brackets, I can't do anything right there. But anytime I'm working inside a function, that's also an implied grouping, right? So we can look at everything under the radical. And I've got x minus 2 quantity cubed plus 5 minus 5. So what happens? The 5's cancel. So now I've got the cube root of something cubed. Well, what does the cube root of the cube do? Cancel. So that looks like x minus 2 plus 2 equals x. Ah, what do you know? Okay, what do you know? All right, so let's go back then and let's look. So what do we get there? We get that inverse functions undo each other. And in order for a function to be an inverse, then this has to be true, right? Both the function of its inverse and the inverse of its function have to undo each other, okay? I'm not going to do it today, but I'll come back to this and I'll show you a tricky one that you think should work and doesn't work. We don't have time today to do it. Okay, let's go back to here for a second. Let's look at some graphical stuff. So if we're given some function and it's even graphed, we don't even have to go through the hassle. Well, I guess we will real quick. So what are tell me what the coordinates are of the ordered pairs that form the inverse of this function. What's first? Okay, so we're going to get negative 2, negative 4. Let's graph that. So negative 2, negative 4 is right there, correct? Okay, what's the next one? Negative 3, 0, so that's right there, right? Next one?
2, 1.
2, 1, so over 2, up 1, and 1, 4. So we go over 1, up 4. Okay, I want you to notice something. What do you notice about the red dots and the black dots? What are they? Say again. Oh, over what? Okay, they're reflections over the line y equals x. Okay, that's must not be an accident, right? It's not. That's true of all inverse relations. An inverse, the graph of an inverse is always going to be the reflection of the original over the line y equals x. Okay, so then what are we going to get? Let's take an example here. What if we wanted to, for example, I'm going to show you a great trick. It's not in the book. What if we want to graph, let's say, start off with cube root or a cube function. So there's my function f of x equals x cubed. The inverse of that is just cube root, right? What's a cube root function going to look like? It's a little bit difficult. It's just not conceptually simple to reflect over a diagonal line. It just is hard for us. It's much easier for us to think about vertical and horizontal reflections, right? So I'm going to show you a little trade that you can do here. Instead of reflecting over the diagonal line, y equals x, you can instead turn that into two steps. The two steps are, first you're going to rotate 90 degrees counterclockwise. Okay, so step one, rotate counterclockwise 90 degrees. So what happens to this then? This is just, everything's going to go like that, right? Rotations are easy to see though. So it becomes like that. Step two is reflect over y-axis. See how that works? If I take that blue one now and I reflect it over the y-axis, what happens? Well, this guy up here just becomes that. This guy down here becomes that. Take your pick. Either or works. You can do one reflection over the line y equals x, or you can trade it for a 90-degree counterclockwise rotation and a flip over the y-axis. Most people like that better. It's a little easier to do. Okay? But think about what that means then. Here's the really cool part of this. This is what I love about math. So now let's think about this. You guys told me at the beginning of the period, you told me that the test to predict whether a relation's inverse is going to be a function is the horizontal line test, right? So let's go back and let's pick, like, for example, a parabola. So if we start off with a parabola, that is a function, but its inverse is not going to be, right? Because look what happens, the inverse, because this function fails the horizontal line test, the inverse is going to fail the vertical line test. Well, let's prove that. All I've got to do is take the function and its inverse and reflect them both over the line y equals x, right? Well, what happens to the function? Let's do it in our two steps. If we take the parabola and we rotate 90 degrees counterclockwise, it ends up like that. Flip it over the y-axis, and we get this, right? What happens to the purple line? Let's just go ahead and take the line with it. If I rotate the line 90 degrees, doesn't the line end up over here? Deflect it over, it ends up right there. Make sense? Right? Okay. How much time we got? Okay, we go. We're gonna. This is good. We'll finish everything up. This is good. Last thing. I wouldn't normally necessarily do all of this stuff, but I wanted to get it done today so we can do the other stuff tomorrow. Yeah. Okay, so we've got, this is just an online interactive lesson. Oops, hang on, I gotta go back.
Recall the relation that this hasn't included anything in this subject. Oh.
Okay, so what about this here? In class, an anatomy student is shown the femur of an adult male. Okay, so, because it's old probably. So the student is asked to measure the length of the femur and then estimate the height of the male.
It's a bone?
Mm-hmm.
Oh my God. Jill, I don't know if you know this, but there's one side to it.
Yeah.
One?
Okay.
What? No, I mean like the bone
right, so we ready? Jill, if you got it, if you need to leave the room, that's fine.
Yeah.
It's kind of. Okay, so the student is asked to measure the length of the femur and then estimate the height of the male from which the femur came. How can the student determine the height? Oh wait, we're running out of time though. Okay, so how could the student determine the height? The answer depends on analyzing the data, of course, finding the lines of best fit, and so on and so forth. But the point of this is, if we've got some function that links height to femur length, what if we wanted to flip that backwards, right? So let's say that we had an equation that given that predicted femur length as a function of height, right? It might be more useful for us to do the opposite though. What if we wanted to instead predict height based on femur length? What would we have to do? So in other words, our function might look something like this. I don't know what it is, but let's just say that we have a function for femur length, which we'll call L, equals f of height. Maybe this guy's an anthropologist and he wants to study the people of this, they're studying an ancient culture or something. And he wants to know about the heights of the people. He would prefer to do something different, right? Because he finds the bones in the ground and he wants to make an estimation of how tall they were. So he wants to instead come up with a function that's going to input femur length and output height. How's he going to do that? Find the inverse. Yeah, right? That's what he's going to do. He's going to have to flip this around by taking the inverse, right? To come up with a useful function for him in his research. Okay? Make sense? All right. You got the goods. You're ready to go.
All right.
I'll put up the assignments.